Welcome. In this session, we'll explore the problem maximum size subarray sum equals k. This problem involves finding the largest subarray whose elements sum up to a given value, k. Let's dive into the problem statement and approaches to solve it. In this problem, we are given an integer array called nums and an integer k. The goal is to find the maximum length of a contiguous subarray within nums that sums up to exactly k. If no such subarray exists, the function should simply return 0. Let's look at the input format. The array nums can contain integers ranging from negative 10,000 to positive 10,000, and its length can go up to 100,000 elements. The value of k can also be a very large or very small integer, ranging from negative 1 billion to positive 1 billion. The output will be a single integer that represents the maximum length of the subarray that meets the condition. If there's no subarray that sums to k, the output will be 0. To better understand the problem, let's explore some examples. In the first example, the input array is 1, minus 1, 5, minus 2, 3, and the target sum k is 3. The output here would be 4, because the subarray 1, minus 1, 5, minus 2 has a sum of 3, and it is the longest subarray with this sum. In the second example, the input array is -2, minus 1, 2, 1, and k is 1. The output is 2, as the subarray -1, 2 has a sum of 1, and its length is 2. These examples illustrate how the goal is to identify not just any subarray with the correct sum, but specifically the longest one that satisfies the condition. In the third example, the array is 1, 2, 3, and the target sum k is 6. Here, the output is 3, because the entire array 1, 2, 3 sums up to 6. This shows that if the entire array meets the condition, its length is returned as the result. Now let's discuss the constraints. The length of the array nums can be as large as 100,000, so the solution needs to be efficient. Each element in nums can range from negative 10,000 to positive 10,000, and k itself can take on very large values, positive or negative. The input array can even be empty, which must be handled appropriately. These constraints guide us toward designing an optimal approach. It's important to consider a few edge cases while solving this problem. If the array nums is empty, the output should be 0, as there is no subarray to consider. Similarly, if no subarray in nums sums to k, the result should also be 0. On the other hand, if the entire array adds up to k, we simply return the length of the array. Additionally, since nums can contain both positive and negative numbers, the solution must handle cases where the subarray includes a mix of these values. This flexibility in the input makes it crucial to account for all possible scenarios to ensure the solution works for all edge cases. To tackle this problem, we first consider the brute force approach. The idea here is straightforward. For each starting index in the array, calculate the sum of every possible subarray by iterating through all potential ending indices. If a subarray sum equals k, we update the maximum length. However, this approach has significant drawbacks. Its time complexity is n squared, as it involves nested loops to calculate subarray sums, making it computationally expensive for large arrays. Additionally, it doesn't use any extra space, so the space complexity is 1. While simple, this approach becomes impractical for arrays where n approaches 10 to the power of 5, as it cannot scale effectively. To address these limitations, we can explore a more efficient solution using a hash map. Now, let's break down the optimized approach using a hash map. This solution leverages the concept of cumulative sums to streamline the process. First, we initialize a hash map that stores cumulative sums and their corresponding indices. We also add an initial entry of 0, minus 1, to handle cases where a subarray starting at index 0 equals k. As we traverse the array, we maintain a cumulative sum variable, updating it with each element. For every new cumulative sum, we check if the difference current_sum k exists in the hash map. If it does, we calculate the length of the subarray ending at the current index and update the maximum length. If the current cumulative sum isn't already in the hash map, we store it along with its index to ensure we always use the earliest occurrence. This approach efficiently identifies subarrays with the desired sum in a single pass, achieving a time complexity of n. The space complexity is also n, as we store cumulative sums and their indices in the hash map. While other methods, like the sliding window approach, might work well for non-negative numbers, they fail to handle the presence of negative numbers in this problem, making this optimized hash map approach the better choice. The chosen strategy for solving this problem is the optimized approach using a hash map. This decision is based on its ability to balance efficiency and simplicity. The key insight here is the use of cumulative sums, which allows us to quickly determine whether a subarray with the desired sum exists. By storing these sums and their indices in a hash map, the algorithm achieves O(1) lookups, enabling us to calculate the maximum subarray length in linear time. This method scales exceptionally well for large arrays, making it suitable for competitive programming and real-world scenarios. When compared to the brute force approach, the hash map method significantly reduces time complexity from O(n)² to O(n). While the sliding window approach is efficient for problems involving only non-negative numbers, it struggles with negative values, which are common in this problem. Therefore, the hash map approach not only handles edge cases, like arrays with zero or negative numbers, but also scales efficiently with large inputs. In conclusion, the hash map approach stands out as the most effective and robust solution for this problem. It strikes a clear balance between time and space complexity, reducing runtime to O(n) while using O(n) additional space. This trade-off is justified by the scalability and flexibility the algorithm offers. Furthermore, it addresses all constraints, including handling edge cases like negative numbers and arrays containing zeros. By leveraging cumulative sums and quick lookups through the hash map, this method provides an elegant and efficient solution to finding the maximum size subarray with a sum equal to k. To solve the problem of finding the longest subarray with a sum equal to k, let's first explore the brute force approach. We start by initializing a variable called max_len to 0, which will eventually hold the length of the longest subarray that meets the criteria. Then, we loop through each possible starting index I in the array. For each starting index, we initialize another variable, current_sum, to 0. This variable will help us calculate the cumulative sum of the subarray as we iterate through the elements. Using a nested loop, we consider every possible ending index j for the subarray starting at I. At each step, we add the value of nums, j, to current_sum and check if it equals k. If it does, we calculate the length of the subarray as j I plus 1 and update max_len to store the maximum length found so far. This ensures we capture the longest subarray that satisfies the condition. Additionally, we account for edge cases, such as an empty array, where no subarray exists, and the result should simply be 0. In cases where no subarray sums to k, the algorithm will return 0 as the result after completing all iterations. After checking all possible subarrays, the value of max_len will hold the length of the longest subarray with a sum equal to k, which we then return. Here's a pseudocode representation of this brute force approach. We initialize variables max_len to 0 and calculate the length of the array, n. Using two nested loops, we iterate over all possible subarray starting and ending indices. For each subarray, we calculate the cumulative sum and check if it equals k. If it does, we update max_len to store the maximum length found so far. Finally, the algorithm returns max_len after completing all iterations. While this approach guarantees that no subarray is missed, it is computationally expensive due to its nested loop structure, which results in a time complexity of O(n)². The time complexity of this brute force method is O(n)², because we use two nested loops to evaluate all possible pairs of starting and ending indices. On the other hand, the space complexity is O(1), since we only use a few variables like max_len and current_sum without employing additional data structures. This simplicity ensures minimal memory usage. The reason this approach works is that it systematically examines all potential subarrays and uses the cumulative sum to efficiently check if the target condition is met. However, the brute force method is not ideal for large arrays, especially when the size of the array, n, becomes very large, such as 10,000 or more elements. To address this limitation, we can optimize the solution by using a more advanced technique called prefix sum with hash map, which reduces the time complexity to O(n). This optimization eliminates the need for nested loops by taking advantage of the relationship between prefix sums and the target sum, allowing us to find subarrays more efficiently. To better understand the brute force approach, let's visualize how it works with a concrete example. Suppose the input array is nums equals 1, 2, 3, 4, 5, and the target sum k is 9. Starting with I equals 0, we check subarrays like 1, 1, 2, 1, 2, 3, and so on. When we reach the subarray 1, 2, 3, 4, the cumulative sum equals 10, which exceeds k, so we stop extending that subarray. As we continue evaluating subarrays, we find that the subarray 2, 3, 4, starting at I equals 1 has a sum equal to k and a length of 3. Repeating this process for all possible starting indices ensures that no subarray is missed. Ultimately, the algorithm identifies 2, 3, 4 as the longest subarray with a sum equal to k, with a length of 3. This visualization highlights the exhaustive but reliable nature of the brute force approach in exploring all subarray possibilities. This Python implementation solves the problem of finding the maximum size of a subarray whose sum equals the target value k. Here's a breakdown of the code. 1. Initialization. Prefix underscore sum keeps a running sum of the elements as we iterate through the array. Max underscore len tracks the length of the longest subarray found so far. Prefix underscore map is a dictionary that maps cumulative sums, prefix underscore sum, to the earliest index where they occur. This helps efficiently check for subarrays that sum to k. 2. Iterating through the array. For each element number at index I, we add number to prefix underscore sum to update the cumulative sum. If prefix underscore sum equals k, it means the subarray from the start of the array to the current index sums to k. Update max underscore len to I plus 1 since this subarray includes all elements from index 0 to I. If prefix underscore sum k exists in prefix underscore map, it means there is a previous subarray whose sum is prefix underscore sum k, and removing this subarray leaves a subarray that sums to k. The length of this subarray is I prefix underscore map, prefix underscore sum k. Update max underscore len if this subarray is longer than the current max underscore len. 3. Storing prefix sums. If prefix underscore sum is not already in prefix underscore map, store it with the current index I. This ensures that we only record the earliest occurrence of each cumulative sum, which is crucial for finding the longest subarray. 4. Returning the result. After processing all elements, return max underscore len as the length of the longest subarray whose sum is k. This approach uses a single loop to process the array, making it highly efficient with a time complexity of O(n). The space complexity is also O(n), due to the prefix underscore map dictionary. This solution handles all edge cases, such as negative numbers, arrays with no valid subarray, and arrays where the entire sum equals k. The use of a prefix sum and hash map ensures that we avoid redundant computations, making the solution both clean and performant. Here, we start by importing the hashmap class, which will help us efficiently handle prefix sums. The method maxSubarrayLen takes an array of integers, nums, and an integer, k, as inputs. Inside, we initialize three variables: prefix sum, which tracks the cumulative sum of elements, maxLength, which stores the maximum length of a subarray with a sum equal to k, and prefix map, a hash map to store prefix sums along with their corresponding indices. The loop iterates through the array, updating the prefix sum with the current element. If the prefix sum is equal to k, it means the subarray from the start to the current index has a sum of k, so we update maxLength to be the current index plus 1. Next, we check if there's a previous prefix sum stored in prefix map such that subtracting it from prefix sum results in k. If such a prefix exists, it means we've found a subarray with the desired sum, and we calculate its length by subtracting the stored index from the current index. We then compare this length with maxLength and update it if necessary. Finally, we ensure the current prefix sum is added to prefix map along with its index, but only if it hasn't been stored before, to preserve the smallest index for each prefix sum. The function concludes by returning maxLength, which holds the length of the longest subarray with a sum equal to k. This implementation uses a hash map to efficiently check for and store prefix sums, making it run in linear time, O(n). By leveraging the relationship between prefix sums, we can determine subarray lengths without having to repeatedly calculate sums for different ranges, ensuring the solution is both optimal and concise. To solve this problem, we start by initializing three variables: prefix underscore sum to keep track of the cumulative sum as we iterate through the array, max underscore len to store the length of the longest subarray that sums to k, and prefix underscore map, a dictionary to store the first occurrence of each prefix sum. In the first iteration, where I equals 0 and number equals 1, we update prefix underscore sum by adding the current number, resulting in prefix underscore sum equals 1. We check if this is equal to k, which it is not. Then we calculate prefix underscore sum k to see if a previous subarray exists that completes the sum to k. Since -2 is not in prefix underscore map, we add the current prefix underscore sum with its index to the map. Moving to the second iteration, with I equals 1 and number equals -1, updating prefix underscore sum gives 0. Again, we check if this equals k, which it does not. We also find that prefix underscore sum k equals -3 is not in prefix underscore map. Thus, we add prefix underscore sum with its current index to prefix underscore map as well. In the third iteration, where I equals 2 and number equals 5, we update prefix underscore sum to 5. This is still not equal to k, and prefix underscore sum k equals 2 is also not in prefix underscore map. Thus, we add prefix underscore sum with its index to the map. In iteration 4, with I equals 3 and number equals -2, updating prefix underscore sum results in 3, which is exactly equal to k. This means the subarray from the start to this point sums to k, so we update max underscore len to I plus 1, which is 4. We also add prefix underscore sum to prefix underscore map. Finally, in the fifth iteration, where I equals 4 and number equals 3, updating prefix underscore sum yields 6. This does not equal k, but prefix underscore sum k equals 3 is found in prefix underscore map at index 3. Using this, we calculate the length of the subarray ending here that sums to k and update max underscore len to the maximum of its current value or this new subarray length, which remains 4. We then add the current prefix underscore sum to prefix underscore map. By the end of this process, the maximum length of a subarray that sums to k is stored in max underscore len, which is 4 for this example. Now, let's look at a second example where nums equals -2, -1, 2, 1, and k equals 1. Again, we initialize prefix underscore sum to 0, max underscore len to 0, and prefix underscore map as an empty dictionary. In the first iteration, where I equals 0 and number equals -2, we update prefix underscore sum to -2. Since this does not equal k and prefix underscore sum k equals -3 is not in prefix underscore map, we add prefix underscore sum with its index to the map. In iteration 2, with I equals 1 and number equals -1, updating prefix underscore sum gives -3. This is not equal to k, and prefix underscore sum k equals -4 is not found in prefix underscore map. Thus, we add prefix underscore sum with its index to the map. In the third iteration, where I equals 2 and number equals 2, updating prefix underscore sum results in -1. This still does not equal k, but prefix underscore sum k equals -2 is found in prefix underscore map at index 0. Using this, we calculate the subarray length as I'd prefix underscore map, -2, which is 2. Since this is greater than our current max underscore len, we update max underscore len to 2. We then add prefix underscore sum with its index to prefix underscore map. In the fourth iteration, where I equals 3 and number equals 1, updating prefix underscore sum gives 0. While this does not equal k, prefix underscore sum k equals -1 is found in prefix underscore map at index 2. We calculate the subarray length as I'd prefix underscore map, -1, which is also 2, so max underscore len remains unchanged. We add prefix underscore sum with its index to prefix underscore map. At the end of this example, the maximum length of a subarray that sums to k is 2. Finally, let's consider a third example with nums equals 1, 2, 3, and k equals 6. We start by initializing prefix underscore sum to 0, max underscore len to 0, and an empty prefix underscore map. In the first iteration, where I equals 0 and number equals 1, updating prefix underscore sum results in 1. Since this is not equal to k and prefix underscore sum k equals -5 is not in prefix underscore map, we add prefix underscore sum with its index to the map. In the second iteration, where I equals 1 and number equals 2, updating prefix underscore sum gives 3. This still does not equal k, and prefix underscore sum k equals -3 is not in prefix underscore map. Thus, we add prefix underscore sum with its index to the map. In the third iteration, where I equals 2 and number equals 3, updating prefix underscore sum results in 6, which is equal to k. This means the entire subarray from the start to this point sums to k, so we update max underscore len to I plus 1, which is 3. We then add prefix underscore sum with its index to prefix underscore map. The final result for this example is that the maximum length of a subarray summing to k is 3. The time complexity of this solution is O, n, where n represents the length of the input array. This efficiency comes from the way the algorithm processes each element in the array. The main loop iterates through the array exactly once, which contributes O, n, to the time complexity. Inside the loop, every operation is constant time. For instance, updating the prefix sum and checking for specific conditions in the hash map only take O1 time. Even the insertion of new entries into the dictionary is a constant time operation on average. When you combine all these constant time operations within a single O(n) loop, the result is an overall time complexity of O(n). This makes the solution very efficient for large input sizes. The space complexity of the solution is O(n), primarily due to the use of a hash map to store prefix sums. In the worst-case scenario, where every prefix sum is unique, the dictionary will store n entries, corresponding to the length of the input array. This is the dominant factor in the space complexity. Apart from the dictionary, the algorithm uses a few auxiliary variables like the current prefix sum, the maximum subarray length, and the loop variable. Each of these requires only constant space, or O(1). Therefore, the total space complexity is determined by the dictionary, making it O(n). When analyzing the best, average, and worst cases, we see that the time complexity remains O(n) across all scenarios. In the best case, the target sum k is found early in the array, but the loop still processes all elements, so the time complexity is O(n). On average, the prefix sums are distributed unpredictably, which means the hash map may store most of them, but the operations inside the loop remain efficient, keeping the time complexity O(n) and space complexity O(n). Even in the worst case, where all prefix sums are unique and the target sum is only found at the very end of the array, the algorithm still performs with the same O(n) time and space complexity. This consistency in performance is a key advantage of the optimized approach. The brute force method, by contrast, is significantly less efficient. It involves generating all possible subarrays of the input array, which requires two nested loops. This results in O(n)² iterations. Additionally, computing the sum of each subarray adds another layer of complexity, leading to a worst-case time complexity of O(n)³. In terms of space complexity, the brute force approach does not use any additional data structures, so its space complexity is O(1). Comparing this to the optimized solution, we see a dramatic improvement in time complexity, dropping from O(n)³ to O(n), while maintaining a reasonable O(n) space complexity, which is crucial for handling large datasets. The mathematical proof for the optimized solution's big O complexity lies in its use of a single loop and efficient data structures. By utilizing a prefix sum and a hash map, the algorithm eliminates the need for nested iterations. Each operation, whether it's updating the prefix sum, performing a hash map lookup, or inserting a new entry, is constant time, or O(1). Since the loop runs exactly n times, the total time complexity is O(n). Similarly, the hash map stores at most n entries in the worst case, resulting in an O(n) space complexity. These optimizations make the solution not only faster but also scalable, making it far superior to the brute force approach for large inputs. When solving this problem, there are a few common mistakes to watch out for. First, many beginners rely on brute force methods, like calculating all possible subarray sums. While this approach might work for small inputs, it quickly becomes inefficient, resulting in time complexities of O(n)², or even O(n)³, which are impractical for larger datasets and can lead to time limit exceeded errors. Instead, it's crucial to use optimized techniques like sliding windows or hash map-based solutions. Another frequent issue is misunderstanding the problem constraints. For instance, if the array contains negative numbers, certain techniques, like sliding windows, may not work unless you carefully adapt them. Similarly, mistakes can occur with the use of hash maps or prefix sums. For example, forgetting to initialize the hash map with a base case, such as setting the prefix sum of 0 at index -1, can lead to missed edge cases. Lastly, overlooking edge cases altogether, like single-element arrays, empty arrays, or arrays where no subarray sums to k, can cause your solution to fail. Thinking through these scenarios and testing thoroughly is key to success. Another challenge candidates face is confusing subarrays with subsequences. Remember, subarrays are contiguous sections of the array, whereas subsequences can have gaps. Solving for subsequences instead of subarrays will lead to entirely incorrect results. Now, let's touch on some key insights for interviews. Recognizing patterns is vital. Many array problems, including this one, rely on recurring techniques like prefix sums, sliding windows, or hash maps. Being able to identify and apply these patterns is a key skill. Also, keep in mind the trade-offs between space and time. For example, while using a hash map or prefix sums can optimize time complexity to O(n), it comes at the cost of additional memory. Interviewers often expect you to discuss these trade-offs. Clear communication is another critical factor. Start by explaining the brute force approach to show your understanding of the problem, then refine your solution step by step, justifying each optimization. Lastly, don't stop at the first solution. Explore alternative approaches and discuss their trade-offs. This demonstrates both depth and flexibility in your problem-solving abilities. To deepen your understanding, it helps to explore related problems. For example, LeetCode 560, subarray sum equals k, is a classic problem that also uses prefix sums and hash maps. The current problem, LeetCode 325, introduces additional constraints, making it a slightly more advanced variation. Other related challenges include LeetCode 3, longest substring without repeating characters, which uses sliding window and hash map techniques, and LeetCode 523, continuous subarray sum, which involves finding subarrays where the sum is a multiple of k. When approaching these problems, different strategies have their strengths and weaknesses. Brute force solutions, while simple, are inefficient with time complexities of O(n squared or O(n cubed, and should only be used for small inputs or as a way to confirm optimized solutions. Sliding window techniques are efficient with O(n) complexity but are best suited for non-negative numbers unless adapted. Prefix sums paired with hash maps offer a versatile O(n) solution for many subarray problems but require extra space. Finally, in some variations, sorting combined with two pointers can simplify the problem, but this approach introduces an O(n log n) complexity, so it's important to weigh whether it's appropriate given the constraints. Great work solving this problem. To recap, we explored different approaches to find the maximum size subarray with a sum equal to k, emphasizing time and space optimization. Keep practicing similar problems to strengthen your understanding. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!